So the first one we have on the concept side, bond types, yes. Electronegativity. So you will have an electronegativity chart available to you. What is the difference between, well, what are the three bond types that we talked about?
Polar, nonpolar, and ionic.
Okay, remember polar covalent. Don't just write polar because ionic bonds are also polar. So it's polar covalent. What does that mean?
Polar is that greater, is that in between 1.7?
Yep, 1.7 to 0.3. But what is it? When you say there's a polar covalent bond, what does that mean? What's happening in that bond? What does covalent mean?
Sharing of electrons.
It means we're sharing a pair of electrons, and polar means it's unequal, right? All right. So there's an unequal sharing of electrons. Nonpolar covalent, if you had a value that's less than 0.3, what does that mean? So there's an equal sharing of electrons.
Is it greater than or equal to?
Yeah, well, I guess greater than or equal to, because if it's 0.3 exactly, you would say it's nonpolar covalent. Same with polar covalent. If it's 1.7 exactly, it'd be polar covalent. To 3.3, yep. So this one has to be greater than 1.7. So let's say it's 0.3. What would it be? It has to be greater than 0.3, but less than or equal to 1.7. Is that correct? And what does ionic mean? So you have a cation and an anion. So there has been a transfer of electrons. From one atom to another. And then now, instead of the bond being the sharing of electrons and electrons holding it together, it's the electrostatic charge holding it together. And creates the bond. Creates. Meaning it's just like magnets, the positive and negative end are held together just because it's charged. So then you might have where you have to determine the type of bond. So let's say you have a sulfur and chlorine bond. You look up your values. And I have this one written down. So 3.0 and 2.5. So what kind of bond would that be? Polar covalent. Just the ionic. What? I think I used a different chart, and they only rounded to 1 decimal place. They have a little different. I don't know. Do you have your chart out? Okay. Let's use your numbers that you have then. It's still polar covalent though, right? Okay. And then it might say which atom is more negative?
Sulfur. I disagree.
Chlorine is more negative. Why? Yes. The electronegativity value is higher. If it has a higher electronegativity value, that means it attracts electrons more strongly. Is that how you say it? More strong? I don't know. Stronger? Attracts them stronger? That doesn't sound. Anyways, it attracts the electrons more strongly and would be more negative. And I think that's it. Questions on that one? So then for ionic bonding, we had this 3-step bonding, or when you show the electron transfer and the formation of the ionic bond, like in calcium chloride. What's the formula for calcium chloride? Yep. So how would this form? Yeah. So first we started with calcium, and how many valence electrons does calcium have? 2. Plus we have 2 chlorines, and each chlorine has how many valence electrons? 7. And then what did we get? We'd have, what happens to these electrons? Calcium gives 1 electron to each of the chlorines. So now chlorine has an octet of 8. So calcium now has no electrons, but what charge does it have? 2 plus, since it lost 2 electrons, lost 2 negative charges. And then it's bonded to the chlorine, which now has, oh, there's 2 chlorine. Let's put that 2 there. And each chlorine has what charge? Negative 1, because each chlorine gained 1 electron. Questions on writing the ionic bonding? Remember, you don't put a dash here because the dash represents a covalent bond. And this isn't covalent, it's ionic. It's because there's a positive and negative being bonded together. And in covalent bonds, when we have 2 chlorines, we would have showed both Cls. And this ionic, you just show the 1, but you have a 2 there showing you have 2 chlorines. Okay, the next one's Lewis structures. I'll just write up, I have 3 of them written down. You can so H2O, what's central? Oxygen, and so we have 2 hydrogens. Oxygen has how many valence electrons? 6. Remember, I'll put the 2 on top and bottom because hydrogens each donate 1 to the bond. Here's the bond, so there's our Lewis structure. How about HCN, what's central? Carbon. And so we'd have hydrogen and nitrogen. Carbon has how many valence electrons? 4, yep. And hydrogen has the 1, so here's a bond. How many does nitrogen have? 5. Probably doesn't matter where I put my 5th one, but I'm going to put it here. So now do we have an octet around carbon and nitrogen? No, we can't add any more dots because we've filled up our electrons. So what do we need to make? Triple bond on this one because this electron and this electron come in here, make a bond. This electron, come here to make a bond, and we have a triple. And this last one, carbon dioxide. Carbon is the center, oxygen on either side. You know we have 4 here and 6 on oxygen. 4, 5, 6. So what do we need to do here? We have a bond. Double bond them both, right? To make it have an octet. bond, double bond. There we go. I know we've done a lot of Lewis structures. Do you guys have any questions on them? Okay, if you have a polyatomic ion, so the next one is polyatomic ions. Let's these two written down to do. So SO4, what does that 2 minus mean? Add 2 electrons, and it can be anywhere. So let's draw SO4 here. Sulfur has 6 valence electrons. So now this oxygen also has 6. Okay, this oxygen needs 6, but since there's already 2 electrons from sulfur, this actually creates a bond here. Let's fill in on the outside first. Six. 1, 2, 3, 5, and 6. So we get to add 2. Where would we add 2? On the left and right here. Yep. So now does everything have an octet? It has 8, 8, 8, 8, and 8. So yep. Polyatomic ions, what do we need to do first, or next? Our last step. Brackets. Then what does this plus mean for ammonia? Take 1 away. So nitrogen has 5. So now this hydrogen donates 1, donate 1, donate 1. And then this hydrogen would donate 1 here, but we need to take 1 away, and there's already 2 here, so we'll just make that a bond. We've taken 1 away already. Put your brackets around, and you have a plus. Via CPR theory. What is the via CPR?
Valence shell, electron.
Valence shell,
Electron pair.
electron pair.
Repulsion, not propulsion.
Repulsion.
We need to know that.
Maybe.
I want to write down a lot of notes. First glance.
So that's just saying that all these valence shell electrons are trying to get as far apart from each other as possible because they repulse each other. And that will determine the molecular geometry. Which will influence the molecular polarity.
So on our tests, will we do polarity and according to the geometry like on the table or the Lewis structure?
The Lewis structure should represent the geometry. So you should use correct bond angles when finding polarity. Okay. So let's just do NH3. N has 5 valence electrons, and then each hydrogen has a valence electron. Like that. So how many atoms are bonded to the central atom? How many lone pairs? So what kind of geometry would it have? Nope. Trigonal, pyramidal. You will be able to use a table. Yes. You don't have to memorize it. What kind of bond angles would you see?
109.5.
So remember, for bond angles, you look back at the geometry of electron, or electronic geometry, how does it say it? Arrangement of electron pairs. You look at that shape and flip it over to the other side, find the bond angle from that side when you have lone pairs. The other class made up one. We knew that one. It was RnF2. I don't think this would really form in nature, but we can draw a Lewis structure for it. So radon has how many valence electrons?
I don't know.
8. So then we need 2 fluorines. So each fluorine will bond to one of those electrons. So it would look like that. And these two, they're actually a pair, so you can leave them separate, or I like to put them over next to each other, just so that you can tell they're a pair. You don't want them to be lonely. So, how many atoms are bonded to it? 2. And how many lone pairs? 3. So what kind of geometry would we see?
Linear, trigonal, bipyramidal.
So it's actually linear, yep. And then when you flip back to find your bond angle, the bond angles would be
120.
and 90. And this one's a little different just because since it is linear, like this would be the 190 and this is another 90. So it could be 180 also for this one, but if you put 120 and 90 down, that would be correct. So you guys want to go over any more examples? You get to use your chart, so. Okay. So let's look at this NH3 molecule since we already had it drawn. We want to find whether that molecule as a whole is polar. What do we do? Okay. First we have to figure out whether it's polar or nonpolar bonds. So you subtract your electronegativity, so you probably will have an electronegativity chart available to you. Polar covalent, okay. And which one's more negative? Okay, so we would draw arrows towards the nitrogen. And since our bond angles are that 109.5, we leave them like this. And do we have an overall polarity? Mm-hmm. And so this one we can, sometimes you see the little sigma plus and minus just showing we have a dipole. That's the symbol for dipole.
So when we were
ASF6 or ASF5. That was one in your lab, I think. So they should be all equal angles from each other. So when you look at this, since they're all equal angles from each other, they are all, when you combine them, going to cancel each other out.
Yes.
So this is all nonpolar. Or if you look at your little chart, what kind of shape would this be? Trigonal bipyramidal, it says right here. And what it has here is there's one on top of, there's the central atom, there's one directly above and directly below. So those two would cancel each other out. And then there's 3 spread out evenly on this plane. And since they're equal angles from each other, they all cancel each other out. So if you look at this picture too, you should be able to tell hybridization. Let's just look at these 2 that we have on here already. We can do some extra ones too, but so NH3, we always start with our S and P or orbitals, S and P orbitals. And how many valence electrons does nitrogen have? 5. So we need 5 arrows, but we have how many lone pairs? 1. So you can start off with making a lone pair here when there's an up and down arrow in the same orbital. That would be your lone pair. And then we need 3 more. which correspond to 3 different bonds. So that would be what it would look like. And what would be the name of our hybridized orbital? sp3. Yep. How about this one down here? We need how many valence electrons? We need 5, right? Do we have any lone pairs? No, so I don't want to pair any of them up. And there's only 4, so I need extra room. So I'm going to go into the D sublevel, and we just need 1 arrow. So what's the name of our hybrid orbital? sp3d. Yep. Let's do a double bond. So carbon has how many valence electrons? 4. And do we have any lone pairs? No. So we'd have it look like this. But since we have double bonds, what kind of bonds do we have? Pi bonds. And we have,
Hey, you guys are loud. Hey. Yeah.
how many sigma bonds? 2. And how many pi bonds? 2. So that means 2 of these do not hybridize, correct? 2 of them do. So these 2 that hybridize we call sp. And then we have these 2 separate. So carbon's in the second energy level, so we say it's 2p, and then you can pick x, y, or z, so we'll pick x. And then also a 2p, z, doesn't matter.
Is it 2 because of the 2 pi bonds?
No, it's 2 because carbon's in the second energy level. So if it would have been silicon instead, that's in the third energy level, so it would be 3p.
Oh, that's my problem. 2p actually.
Because we have 2 pi bonds, so we have 2 that do not hybridize.
So then, germanium.
Germanium would be 4. Yes. You guys know how to count up sigma and pi bonds, right? All single bonds are sigma bonds. And then each double bond has 1 sigma and 1 pi. A triple bond has 1 sigma and 2 pi. 4 intermolecular forces. So what are the 4 intermolecular forces? Dipole, dipole. Ion dipole. Dispersion, I heard. So what is a dipole-dipole force? They're between what? Oops. Between 2 polar molecules. What about an ion dipole? Ion and a dipole is on a what? Polar molecule. Okay, there's actually 3 types of dispersion forces. One is the dipole-induced. I have an ion-induced. I should put induced dipole. And then I think your book just called the other one dispersion. I don't know that it has a. So a dipole-induced dipole is between what? Yep, a polar and nonpolar molecule. C. How about an ion-induced dipole? Ion and nonpolar. And then dispersion force? Oops. 2 nonpolar. And these are always the weakest. Dispersion forces, like any of those three are weaker than the other three. They had to do with polar molecules. Okay, and then hydrogen bonding is between, oops, forgot an E. The hydrogen of one molecule and the nitrogen, oxygen, fluorine of the other molecule. So the hydrogen's on one molecule, the nitrogen, oxygen, fluorine is on a different molecule.